Hello everyone, my name is Signolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome back to our video lesson on exponential functions. This is the second part of our lesson on exponential functions, and in this part of the lesson I want to focus on a couple of things that have to do with the exponential function. Okay, so remember that from our previous video we had the standard form. We had what I called the original form for the exponential function, and the original form is the form that you see here. Y is equal to a to the power of x. This is the original form. I call it the original form because it's the simplest form that you're ever going to get for your exponential function. Okay, we are going to make amendments and we're going to add some changes. We're going to add some things in this exponential standard form or the original form to make the graph behave a certain way. Now, the main aim of this video is to investigate the different ways that the graph can behave when we make additions or when we make changes to this original form. Okay, so we're not going to fundamentally, we're not going to change the original form. The shape of the graph is going to stay the same, but we will see what is going to happen when we do certain things. Okay, so the shape of the graph will generally stay the same. It will generally follow the same pattern. The shape itself might not be exactly the same. In fact, it will not be exactly the same, but the pattern will be exactly the same. You will see what I mean as we progress into this video. Okay, so let's do that. Now, just to recap what we covered on the previous video, you will remember the following. When you draw your Cartesian plane, just remember to always label your Cartesian plane, your x-axis and your y-axis. Okay, remember that the original graph looks like that. The graph from your original equation looks like that. Okay, and the two important factors that we should remember from that original graph is that the x-axis is your asymptote. Okay, the x-axis is your asymptote and the y-intercept is 0 and 1. Okay, when x is equal to 0, y is equal to 1. And the tendency, the pattern that this graph follows is that as we move to the left, the graph gets closer and closer to your x-axis. Okay, and your x-axis is your asymptote. Remember, the asymptote is the imaginary line that the graph approaches but never reaches. Okay, so it gets closer and closer and closer to the x-axis, and that's just why your x-axis is your asymptote, or your asymptote is the horizontal line that passes through y is equal to 0. Okay, so if you want to look at it like that, there's an imaginary line sitting directly on top of your x-axis, and that is what your asymptote is. Okay, so your asymptote lies directly on top of your x-axis, or your asymptote is your x-axis. Depends, doesn't matter how you want to see that. Okay, and your y-intercept is that at 0 and 1. Okay, so as your graph moves to the left, it approaches your asymptote. As your graph moves to the right, it moves further away from your asymptote. And not only does it move further away from your asymptote, but it moves away at an accelerated rate. Okay, it moves away at an accelerated rate. Okay, so you will notice that that point versus that point, the difference is quite huge. Okay, so it moves at an accelerated rate. Okay, so these are the characteristics that I would like you to remember for the previous or for the original. Okay, so keep this in your mind, remember it, do not forget it, because we will be using it throughout this video over and over again as we make changes and additions to our original form. Okay, so let us go on ahead and consider a couple of things. Now, I'm going to consider a couple of things. We're going to consider a couple of amendments to our original form and see what happens to that graph as we make those amendments. Okay, so remember the original is y equals a to the power of x. Okay, so this is the original. Now, the amendments that I want us to consider, the amendments that I would like us to consider for this graph are as follows. What would happen if, let's say, okay, let me just pick my black ink again. Let's say we have y to the power of a to the power of x. But this is the original form. You notice that this is still the original form. But instead of just having it like that, what if I've got b there? Okay, b, let me just write it nicely. B times a to the power of x. This is the first form that we are going to consider. Okay, what's going to happen if we've got y is equal to b times a to the power of x? Okay, now the third form that I want us to consider is we still take the original form. Y is equal to a to the power of x. But what would happen if we said plus c? If we added a plus c there, what would happen to the shape of our graph? How would our graph behave? What would we end up with? Okay, and then the fourth form that I would like us to consider is y is equal to a to the power of x, and let's say on top there I say plus d. Okay, what would happen to our graph if we do that? Okay, now notice that for a, b, and c, they could be both negative or positive. Okay, so b could be positive and negative. We're going to look at that. And then c could be positive and negative. We're going to look at that. And then d could be positive and negative. Okay, so all of these could be both positive or negative, and then we'll study the behavior of the graph when that is the case. And I want you to also keep in mind that all of these can be combined. Okay, so although each of these three different additions will affect the graph differently, we can combine them into one equation so that all the behaviors can be illustrated in one graph. Okay, I will also illustrate what that means throughout the course of this video. So let us go on ahead. Let's start with the first one. The first one is the when we add a b in front of the original form. Okay, so let's get started. So what happens? Let's say we've got y is equal to b, okay, times a to the power of x. What's going to happen to our graph? Well, remember that our original graph, I'm actually going to sketch the new graph that has a b in it in blue, and then the original graph I'm going to sketch in black. Remember, the original graph looks like that. It looks something like that. Okay, it looks like that. Now remember, the original graph has 0 and 1 there. That's the y-intercept. Okay, remember that it has 0 and 1 there, and it has the asymptote here. Okay, asymptote. I'm going to say ASY for asymptote. That's our asymptote. I'm just going to call it as SAY. Okay, that's our asymptote. Now, what would happen if I added that b, that coefficient of b, in front or behind our equation? Well, let's use an example. I think the best way to illustrate these things is through an example. Okay, now let's say I've got this side, I've got two columns. I've got a column, okay. On this side, I've got y is equal to a to the power of x. And on this side, I've got y is equal to b then times a to the power of x. Okay, to the power of x. Okay, so, and then I've got this okay, I've got that, and I've got that, and I've got x here, and I've got y here, and I've got x here, and I've got y here. I'm not going to use a lot of numbers to demonstrate this. I'm just going to use maybe 3 or 4. Okay, so what would happen for this equation here on the left, if x is equal to minus 1, y is equal to a to the power of minus 1. Okay, now let's say a is 2, right? Let's make a 2. Okay, so what I'm going to do is I'm going to say that I'm going to erase and that I'm going to erase, and then I'm going to replace them with 2's. Okay, so that's 2 to the power of x, and that's 2 to the power of x. 2 to the power of x. Okay, and then I'm going to erase that b there. Then for b, I'm going to put in, let's choose a random number, 3. Okay, 3. Okay, so what's going to happen if, okay, so I wrote down in the standard form first so that before I actually put down the actual numbers, you could identify which form is which. Okay, so this is our original form, and this is our amended form or our new form. Okay, so it's just an addition or amendment to the standard form. Okay, so if x is equal to minus 1, you will agree with me that y will be equal to 2 to the power of minus 1. Okay, and 2 to the power of minus 1 is half, right? That's 0, 0.5. Now, if x is equal to minus 1 here, you will agree with me that y is equal to 3 times 2 to the power of minus 1, which is 3 times half. Okay, so it's 3 times half. So then 3 times half is 1,5. So that's going to be 1,5. Okay, that's going to be 1,5. Right. Now, what would happen if x is equal to 0? Well, y would be 2 to the power of 0, and you will agree with me that that's 1. That's 1. Okay, if x is equal to 0, then you will agree with me that y here is equal to 3 times 2 to the power of 0, which is equal to 3 times 1, which is the same as 3, right? 3 times 1 is 3, so then the answer here will be 3. Okay, what happens if x is equal to 1? Well, you will agree with me that y is equal to 2 to the power of 1, which is 2. And if x is equal to 1, you will agree with me that y is equal to 3 times 2 to the power of 1, which is 3 times 2, which is 6. Okay, which is 6. So that is 6 there. Okay, let's do one more. If x is equal to 2, y in this case will be 2 to the power of 2, and that's going to give me 4. If x is equal to 2 here, y, you will agree with me, will be 3. It will be 3 times 2 to the power of 2. Okay, which is 3 times 4, which is 12. Which is 12. Okay. Now, notice, oh, it's not 4, it's 12. It's 12. Okay. Notice what happens. Notice the trend. Notice the pattern. Okay, so for the original form, these are the values that I'm getting. For the original form, those are the values that I'm getting. For the amended form, these are the values that I'm getting. Okay, so now you will notice that the y values for the amended form or the new form or the changed form are 3 times the values that I got for my original form, right? 0,5 times 3 is 1,5. 1 times 3 is 3. 2 times 3 is 6. And 4 times 3 is 12. Okay, so how does this affect our original graph? Our original graph is 2 to the power of x. You can see the original part of the graph there. It's 2 to the power of x. Well, clearly this 3 increases by our original graph by a factor of 3. So all the y values of our original graph are increased by a factor of 3. Okay, or a factor of the number that we add behind the original equation, which is 3. So in this case, if I go up there, If I go up here, well, clearly we've just established that if we add a factor, okay, so this factor that we just added here, this coefficient that we added here, the only thing that this coefficient does is that it increases our graph by a factor of itself. Okay, so by a factor of b. If we add b, then the y values for this graph will all increase by a factor of b. This includes the y-intercept. Okay, so the y value for the y-intercept is 1 for our original graph, meaning that the y value when x is equal to 0, the y value, in fact, let me use blue. The y value for our new graph will be, x doesn't change, x is 0, but y will be 3. Okay, so the y-intercept for our new graph will be at that point there, up there, and then our graph will do that. Okay, where this graph goes up by a factor of 3. So all the points on this graph go up by a factor of 3. All the points in this graph go up by a factor of 3, and that is how b affects our graph. Okay, all the y values go up by a factor of 3, so that the y-intercept there is 0 and 3. Okay, so this is how our graph is affected. So look at it. Let's look at a couple of examples, quick examples. Let's say you've got y is equal to 2 times 2 to the power of x. Well, you will tell me that the y-intercept of this will be 0 and 2. If I were to quickly sketch that, this would look like that. Okay, look like that, where the y-intercept would be 0 and 2. Okay, because 2 is the number behind the original form. That's behind the original form there. Okay, so another example, let's say you've got y is equal to, I don't know, 17 times 7 to the power of x. This, you would tell me, would look like that, right? Where your y-intercept there would be 0 and 17, because that number there before the original form is 17. Okay, now I want you to notice that the asymptote stays the same. The asymptote is still your x-axis. The asymptote doesn't change. Okay, your graph still approaches the x-axis without reaching the x-axis. Your graph still approaches the x-axis without reaching the x-axis. Your graph, even for this blue one, still approaches the x-axis without reaching the x-axis. Okay, so this is still your original graph. It's just that the only difference that adding that b there has made is that all the y values that you get have been multiplied by 3, but it still behaves the exact same way as your original graph. Okay, so this is how b changes your graph. Okay, that's how it affects your graph. So remember from the original graph, and let me just go back up there. Remember from the original graph that your y-intercept is 0 and 1, and your asymptote is your x-axis. Now the only thing that adding b has changed is that we've changed your y-intercept, but we've kept our asymptote the same. Our asymptote has not changed, it's still on your x-axis, but your y-intercept has changed, and it's become different from your original. So your y-intercept for this standard form, we've got b times a to the power of x. Your y-intercept is 0, x stays as 0, and then your y is b. Okay, so this is the main change, this is the change that this new form effects on our graph. Okay, so I will cover the rest of the, I think I should cover the other changes on separate videos so that we keep this video just for this form. Okay, so I will catch you on the next video for the rest of the other changes to the standard form. Till next time. Lesson number one, lesson number one. Lesson number one, lesson number one.